Hi and welcome to today's session on agent-based computer simulation. Agent-based modeling part 2. During part 1 we already got our hands dirty and played around with some agent-based computer simulations and that's the best way to get to know anything, including and especially if it's something as intuitive and as much fun as computer simulations. So now that we have a basic rudimentary understanding of what this is actually about, today I want to take more like a 10,000 feet bird's eye view to reflect on the general outlook of this specific scientific method. So if we place it into the bigger picture of our computational scientific methods, what we will not do today is deal with empirical data. So we don't observe reality. We also won't analyze this kind of data through some kind of analytical tool. We will be in the realm of theory, of theoretical explorations of societies and their systems through this kind of, well, modern theoretical tool, doing formal theory step by step through these through code. And we will do that as always, as usual, with 3 questions. The first question is, what are some of the characteristics of agent-based computer simulations? Second, what are some of the outcomes? And we'll see there are certain classes of outcomes that we can expect of agent-based computer simulations. And last but not least, what are some of the critiques of agent-based computer simulation? That's very important, especially when you do research. I have to tell you, the researchers are among the most self-critical people of everybody you could ever work with. I mean, as you know, I worked most of my life before joining academia. I worked for 15 years outside of academia. And it's not very common in the industry or in government that you meet people who tell you what's wrong with their approach or with their idea or with a product or service. Usually, that's usually swept under the rug a little bit, right? But in academia, you will see every research paper, every article ends with the researcher reflecting for himself or herself what's actually wrong and critique it. And it's a very open critique in the research community in general. So we will talk about some of the critiques after having talked about all the wonders, and also how we could face and respond to some of these critiques that are common for this particular scientific method. Let's start with the first question. What are some of the characteristics? And I will run through 4 characteristics. First is agent-based, the fact that it's agent-based computer simulation. Second of all, I will show something quite intuitive, and that it is quite intuitive. Having played with some of these agent-based models, you can see that yes, it's an intuitive way also to communicate some often counterintuitive result. Third, it's modular. That comes from the coding, from the software approach, which enables that we can adjust it to different contexts. And fourth, that it's probabilistic, inherently probabilistic, as actually every serious scientific method has to be inherently probabilistic. Now, agent-based models make that very clear, and that introduces a certain kind of humbleness, because we don't have the truth. We can only say what could be likely. Let's start with the first one, with agent-based emergence. We already seen that in computer simulations that are agent-based, there are 2 things that can be happening. One is the macro can be surprising, the big picture, the big dynamic can be surprising, or the micro can be surprising. That means the behavior of the individual agents. That's because we have these individual agents. So for example, in shelling, we saw bottom-up, we programmed the individual rules of the behavior. We knew they're tolerant people, and then we saw surprising macro outcomes on the social level, segregation. The other way around on Sugarscape from Epstein and Axtell, we saw that there are quite intuitive observed social patterns like an unequal income distribution, and it was actually quite surprising how easy it is to replicate that with some very justifiable and intuitive behavior on part of the individuals. And what's between the macro and the micro, that's actually what's often referred to as social emergence. So this higher level emerges from the lower level, and then on this higher level there are kind of like its own rules, and you can do science only on the higher level as well, because there are some patterns that are detectable thanks to the predictability that merges out of these individual behaviors. And that is something that has fascinated social scientists since the beginning of doing social science. So philosophy, sociology, economics, political science, and this gentleman here, everybody claims he belongs to them. The sociologist, the economist, the political. Karl Marx really thought very deeply about many things. And he has this famous one at the end, became known as the basic metaphysical principle of dialectic. And he said, merely quantitative differences, so quantitative differences beyond a certain point pass into qualitative changes. So you add and you add and you add, or you take away, you take away, you take away, or you hold, and this time just passes and passes and passes, and suddenly something qualitatively different happens. And this is known as a phase transition, then, for example. Means that we go into a qualitatively different phase of the social dynamic. For example, we make a little change, and we saw that in Schelling, and certainly segregation is not such a big issue anymore. Or we make a little change in some policy, and suddenly income inequality is not such a big issue anymore, right? And there's these tipping points that can push these systems. Now, where these phase transition often comes from the interdependency of the individual actors. That's why it's very important to model the individual actors, to actually get these interdependencies and have these emergent phenomena. Many of them are phase transition nonlinearities, but not only, sometimes it's also just really unexpected what happens on a higher level or what happens on a lower level. But in order to understand this, what we call here social emergence, that actually is something that all social scientists are really at the end interested in, is the fact that we have individuals that interact and create something bigger, and the something bigger is to some extent predictable. That's why we can do social science, treating society as kind of like one living entity that behaves a different way, organizes a different way, satisfies its needs a different way, and different scientists who research different aspects of that, well, call themselves there in different disciplines. How you satisfy your needs, it's called economics. How you govern yourself is called political science, and so forth. But at the end, social scientists are interested in these emergent phenomena. So it's extremely important to actually account for the individual actors and their interaction, which makes this emergent phenomena. And that's something actually pretty new. And that's why it's called agent-based computer simulations. Computer simulations have been around for a long time, as you can see here, for example, from simulations from engineering. So engineers have simulated buildings and bridges that didn't exist in empirical reality on their computers for many decades, in order then to see, well, how would they hold in order to study them before they would spend all this money in building them. Traditionally, these models and these simulation models coming out of systems theory have been based on factors. What are factors? Factors are already aggregate variables that describe something. So for example, if you want to understand how to build the outline, kind of like the calendar, the schedule of how to build a building, you need to consider things like the weather, the schedule of delivery of the material, the work hours input that you have available, the price stability, and so forth. And then combining all of that, the weather, which affects the delivery of the material, the price stability, which also affects it, which then affects the working hour input. And then you can build this building sooner or later. And once you have a relationship among these, you can set up your schedule, as you can see here, and walk through and plan with it, and so forth. So in social science, we also do this. We work a lot with factors. We have other factors. For example, you can have the genetic composition of an individual, its location, and its skills, and that will then tell you something maybe about the income of this person. That, for example, the metabolism, then the location of this person, where it's located, urban or rural, for example, the skills, the vision, and that would then determine the income. You don't have to model individual actors to do that. You can just have a model just like this, do a correlation model, for example, among these variables, among these factors, and see how we can predict something like income. Now, these variables are usually taken as averages. So your average location, your average skills. Now what we saw actually, we modeled agents, individual agents, with a distribution of metabolism, of vision, of location. We put everybody in a uniquely different location actually. And that makes a difference. It makes a difference if you say 20% rural and 80% urban, or if you put each one in a unique location. So these emergent phenomena that come out of that are different, and often you cannot produce these emergent phenomena, you cannot replicate them if you don't have this agent-based diversity. Let me give you a toy example of that we can actually trace through and play through and see what's the importance of these averages. So this is a model from Granovetter. The Granovetter is the same Granovetter as the strength of weak ties from the networks. And he has a riot model. And the idea, basically, the question that he had there is, how do riots start? Or, for example, panic in public places. So imagine you would be in a mall and you stand in this mall and suddenly somebody starts running. You'll probably say, okay, this person starts running, maybe you even turn around and look what's going on there. Maybe he has to go to the bathroom, or maybe something, or I don't know. Now, what if 2, 3, 4, 5, 10 people would suddenly start running? What would you do? Well, at least you would ask, like, well, is Elvis in the parking lot? Or is, oh my goodness, or something, right? What if almost everybody around you would start running? Well, you very likely would start running too immediately, even so you have no idea why you would start running, but you would, right? Out of social cohesion, social pressure, actually, you might call it, or just because of their own fear and you're following your peers. So now we could model, and that was the question, that was the setup of this model, and he tried to understand when these tipping points happen, when something like this, like a mass riot, which is actually an emergent phenomena, or a mass panic in a public place, when that happens. So let's go here with this toy model, and I gave you 11 subjects here, and the average panicking threshold is 5. That means if 5 people panic, you're in the mall and 5 people around you panic, you will also panic. If 4, you stay put. If 5 or 6 or 7 or more, yes, you also keep on running. Right? So, okay, the first one leaves, nothing would happen, right? 5 people would leave. Okay, so that's the average riot level of these 11 people is 5, and all riot at once when at least 5 leave the mall, leave the building, before nothing happens and suddenly everybody leaves. What if you bring in some agent-based diversity? Now we bring in maximal agent-based diversity. Everybody is different. Everybody has a different rioting threshold or panicking threshold. So the first one leaves of our 11, and then the second one has a panicking threshold of 1. Then the third one, the clown, of 2. The Jasper of 3, the astronaut of 4, the princess 5, the Nicholas 6, and so forth. You keep on going, and each one has a consecutive higher rioting threshold. What would happen in this case? Well, everybody would leave the building, right? The first leaves, then the second leaves, the third leaves, then the fourth leaves because 3 already left, well, then the fourth leaves, and so forth. So now, be aware that the average of them is also 5. Feel free to check for that. So if you sum that up, 1 plus 2 plus 3 plus 4 divided by 11, you also get an average, a threshold of 5. So their behavior is very different. So if I would have taken averages, I could not have distinguished, is it the first or is it the last one? I could have not explained why the one In the one, continuously people start to write. In the other one, nothing happens and then suddenly something big happens. So just working with the average doesn't actually work. Now, the interesting thing is what Scott Page often calls the interesting in-between. That's where social systems most often, or complex adaptive systems in general, most often find themselves, is in these interesting in-between. So you have a diversity of writing thresholds. So in your agent-based model, you would program a certain percentage of your population with this kind of characteristic, another smaller percentage, a bigger percentage with some other characteristics, and then see what happens, just like in society. We're not a continuum between everything. We are also not all the same. We are somehow similar, but also somehow different. And there are groups of us which are more similar, and that's the interesting between all being homogeneous or all being extremely different. What would happen in this case? So the first person starts to run in the mall. What would happen now? Feel free to count through it. So the first person leaves, then the next 3 people in the blue shirts, they have a writing threshold of 1, so they will also leave. Now 4 people started to run. The first one and the other 3. So the astronaut has a writing threshold of 4, would also leave. That means together there are now 5 people running. That means the princess's writing threshold of 5 would also leave. So if we have 5 and 2 princesses, we have 7 people. What would happen now? It would stop here. It would stop after the princess because the next has a writing threshold of 8, not of 7. So here it would stop. It's kind of like a firewall. You see these firewalls also in social systems. Sometimes we want to create these firewalls ourselves. For example, when banks start to default, credits start to default, and banks start to go bankrupt, we want to build firewalls where this contagious effect stops, where it doesn't continue, with spread of disease as well. And it's good that we have this diversity where we try to where we have this diversity naturally. Well, that's a good thing because these firewalls often happen. Or we try to create these firewalls artificially by creating these blocks that are just a little bit bigger, so this effect or negative effect cannot spread further, and at least it stops here. We have a pause to be able to think about what happens next, and then we can keep on going. Maybe it's a positive thing that spreads, and we want to keep it going, but it's good to have a second to reflect on it. So that's what these firewalls. And where does it come from? Well, it's from the interesting in-between of the diversity of the agents. As you can see as well, even in this middle model, and feel free to check for that, the average threshold of these 11 individuals is 5 again. That means if I would just work with the average factor, with the average of a variable, I couldn't distinguish the first behavior, nothing happens, everybody suddenly runs. The last behavior, continuously something happens. And the middle behavior, something happens and then it suddenly stops. I couldn't distinguish it if I wouldn't have the diversity of the agents. That's why some researchers have started to talk about the flaw of averages. That's a word game on the law of averages, which has been very dominant in doing science for the last 200 years. And now about the flaw of averages. As you can see here in this image, it says, well, the average depth of this pond is 3 feet. Well, the average one, you can still drown in it if it's an average and it looks exactly like this. And that's because the averages, as you saw in Granovetter's riot model, can be very deceptive. And that's why often these big events, for example, when something big happens, come unexpected. Because if we only work with the averages, we don't understand the interactivity of the kind of like diverse agents which lead to, for example, these big events, these bursts, these nonlinear changes, where quantitative differences suddenly lead to something qualitatively different, and that for social system is extremely delicate. For example, in this cartoon, somebody goes on the phone and says, I have a stock that could really excel. Well, somebody else, a little bit different, here is like, really excel? And then somebody a little bit different changes like, he said sell, everybody sell. Everybody sells. And somebody says, well, this is madness, I cannot take it anymore. Goodbye. Say, goodbye? Did he say bye? Did he say? And it changes a little bit. It's not completely different. It's not completely the same. It's like the telephone game in this case, but it's a metaphor for the diversity of it. It's the interesting in-between of diversity, which then leads to the fact that everybody says, buy, and the stock market crashes and flourishes, right? So that comes from the interdependency among individuals which are not completely different and not completely the same. And that's why we find these busts and nonlinearity so often in social systems, these phase transitions. So phase transitions, again, you can see them in all kinds of sciences. For example, in water, you see them. Something quantitatively changes. You heat water, nothing happens, and suddenly at 100 degrees Celsius, water becomes vapor. Something qualitatively differently changes. And you take water, you cool it, 50 degrees, 40 degrees, it's still liquid, nothing happens, and at 0 degrees Celsius, suddenly it becomes ice. There's something qualitatively different. In social systems, you see these nonlinear phase transition, tipping points, revolution. To say it in the words of the evolutionary economist Schumpeter, he says, the history of capitalism is studded with violent bursts and catastrophes. We come to the conclusion that evolution is a disturbance of existing structures and more like a series of explosions than a gentle through incessant transformation. So he says actually the history of evolution of society, and his book is also on democracy and society in general, governance systems, and the economy, of course, says, well, it's bursts and catastrophes and explosions that you often see, revolutions that you often see. And to give you a more modern reference from a few years ago, from one of the most cited social scientists that we have these days, Barabasi, he wrote this book called Bursts, the hidden patterns behind everything we do, from your email to bloody crusades. So you often have these bursts, these nonlinear interactions. Now be careful. Say it in the words of John von Neumann and Stanislav Ulam, is using a term like nonlinear science, these nonlinear revolutions, is like referring to the bulk of zoology as the study of non-elephant animals. Which means, yes, there is something nonlinear, there is a phase transition, there is a tipping point, but we cannot really say much about it. Actually, there's only one thing that's linear, which is linear, and there's an infinite number of things that are non-linear. So it is not clear, and we really need to study that more. That's why agent-based diversity is so important, because we have a lot of work ahead of us to understand these busts and bursts and revolutions and tipping points, because there's so many different ones of them too. Now we have an idea where they come from, because we know they often don't come if you just work with averages. So they come from the interdependency of interestingly in between diverse agents, but that doesn't mean that now we can completely predict them, or that we know there are only two kinds of them. No, there's an infinite number of ways you can have these non-linear phase transitions. So a lot of work ahead of us. All right, so that takes care of our first point, the agent-based emergence. As you probably already have noticed, emergence is one of my favorite topics. So there would be a lot more to say about that, and a lot more to say about what we don't understand about it. But as I hope I showed, that's actually what social scientists are really interested in at the end. That makes society what it is, a society, an emergent phenomenon. All right. Let's move on to the next one. Another characteristic of agent-based computer simulation is that it's also very intuitive. And you've seen that. So for example, if we have here Schelling's model, it was quite intuitive, right? We walk basically through it, and you can see then here there are the red and the green agents, and we had these conditions of the similarities, what they want. They wander randomly around, trying to see if they find a spot, and by that, very quickly, you can see, well, it's completely segregated. Wow, interesting. And now you can look under the hood and open it up. And it's quite intuitive. You show that to somebody, even somebody who doesn't do social science. And yes, that's interesting. You can see it, and it's like, okay, you build it. You can explain it now. Now, how did people do that before they had computers to run through that as fast? So here's how Schelling did it back in the late 60s and the 70s. Here he is with his Nobel Prize, which he really earned, because he did that with pennies and dimes. Like really, he sat down with pennies and dimes and kind of like had the heads and the tails and moved them, and then when they were the same, and he counted how many there are, and then he moved them along, and then he see how many are there from this, and you really gotta be a nerd. Like so he really earned his Nobel Prize of that. So in his own words, to say that, he said, "I cannot too strongly urge you to get the dimes and pennies to do it yourself. There's nothing like tracing it through for yourself and seeing the thing work itself out. In an hour, you can do it several times. And experiment with different rules of behavior, sizes and shapes of boards. And if you turn some of the heads, some of the coins' heads and some tails, subgroups of dimes and pennies. Have a fun Sunday afternoon, I would say." But at the end, he brought out these graphs which really convinced people, and it was a very amazing insight that he had. Well, I prefer to do it in NetLogo, but yes, you can do it like this, just by hand as well. And that's how people did it before. It's just extremely work intensive. And some of the things that we're doing with computer simulations, impossible. You could do it with dimes and pennies. Another alternative, so this would be called a numerical solution, kind of like you run it just like he did at the beginning with pennies and dimes and simulated different runs. You can do an analytical solution of that. So this here is from Sam Bowles, a traditional book on microeconomics, and that's what the equation actually looks like. So that's the equation basically for Schelling's model. And this can be read as follows. The equation may be read as follows. The expected fractions of green next period is the fraction of green this period minus any green who sold or exchanged position with a blue, the second term on the right, as you can see, plus any blues who sold to a green, the third term on the right. So what you do then, you take your derivative, you maximize it, you see if it's larger than 0, and here's the optimum we find in equilibrium. Mr. President, I just need $10 million to do a neighborhood project that fights segregation, and my justification is this, which probably nobody in the room understands, maybe the intern, who happens to have a math background. But so I worked in public policies, as I said, for 15 years, and it would be hard to convince a policymaker, especially if you have something new. I mean, if it's an equation that is known, and by now Schelling's model would be known also to policymakers, and there's a Nobel Prize behind it, yes, people can be convinced. But if you have something new to see, showing just a computer simulation, also for policymakers, they can play with it. It's very intuitive. You can communicate the idea very well. And to my experience, when you show that to policymakers, they want to start playing with you. They kind of like become social scientists. They're like, they're starting to throw hypotheses at you. Saying like, oh, what if we would change this and that? Like, what would happen then? It's like, but we don't have to do any math. Let's just try it out. And you try it out in front of them. They gain some ownership with it. It's not like they are scared of it or don't really know and don't trust it because they don't understand this complicated math. It's not like I have to say, like Schelling, I cannot urge you, please try it out for yourself. Just in a few hours you can. No, you can in real time show it to them and make a convincing argument. So that's a very big advantage of these kind of computer simulations, that you have an intuitive communication tool for your policy advice. This brings us to another point, which is also very useful if you use science to do policy recommendation. Policy, I also don't mean only public policy. It could be, if you're in a company, you have to convince your CAO or the board of the company if you have a big project in mind. So it could be strategy building as well, policy. It could be private sector policy as well. And that is modularity and the context scalability. And that comes from the fact that software code, programming code is modular. So think about it this way. For example, here I have a simulation about traffic. Now that's a very rudimentary simulation about traffic, but it simulates something extremely important in traffic, and that is the acceleration and deceleration and the slight diversity in acceleration and deceleration in cars, which leads to the fact that since there is this slight diversity of acceleration, there are these lags and it builds these waves. Did you ever wonder if you're on a freeway, like on a big freeway, and suddenly all cars stop? And you wonder, why is that? Is there an accident coming up or something? And then you go the entire way through and you never find an accident. You never find anything big, but still cars, like literally just 10 minutes ago, you were standing still. Like, why is that? Why is it not flowing? So that comes from this diversity, not complete diversity and not complete homogeneous, interesting in-between diversity of acceleration, deceleration. And here, if you look at this simulation, you can kind of like see how that happens, right? And you can simulate that, convince yourself with it, convince yourself of it, how that actually works. I encourage you to do that. It's very liberating. So next time when you're in the traffic jam, you start to understand, like, actually, wow, it's not only this one. You get so upset about other people. No, you start to realize, oh, I'm part of the problem too, because my diversity contributes to the fact that this complex social adaptive system actually. So it's quite liberating to do that, and you don't have to get so upset anymore next time you're stuck in a traffic jam. But here, that is something very important that leads to traffic jams, but it's not the entire phenomena. Now we can scale that up to a bigger scale and have now the same code and build a grid. So we just took now exactly the same code that we had before and just put it in a grid. And we still have the slight diversity in acceleration and deceleration, and we put traffic lights in too. Now we have traffic lights in, we can see how we could place these traffic lights, how we could time these traffic lights. Nobody gets affected in the real world. We don't have to experiment with people in town. Just do that on a computer and see how should we actually turn on and off traffic lights if we assume, and we can calibrate the acceleration, deceleration from empirical data, we can inform it with that. And if we assume different kind of rates, how would that then actually work? But we did that based on the previous code that we already had. So we just then, if you have a piece of code, what do you have to do to replicate this piece of code? Yeah, copy paste. Right mouse button, copy paste. There are infinite economies of scale in digital code. And so you can just do that and then copy it 1, 2, 3, 4 horizontal, 1, 2, 3, 4 vertical, put it in, and then you already have it. And on a higher level of emergence, something different will now happen. Now you can also go one step further, and that is a traffic simulation from Chicago, and really put it in the city. But you have a lot of building blocks already. And that's very important for policy advice. One big thing, when I worked in the United Nations, one of the biggest critique is that you cannot come with this one-size-fits-all solution, especially if you're confronted with something like the world, which is extremely diverse. So something that worked in one country will not necessarily work with in another country, and especially I had to be very careful with that because, honestly, the world is not really waiting for a white male to come and tell them what to do, right? So you have to be very culturally sensitive if you do this kind of work and study the local conditions, actually. Now, if you have an agent-based model like this based in code, you don't have to start at zero. Because, well, some of the assumption of acceleration, deceleration, yeah, they will be the same in all countries of the world, in all localities. And you can work with that. You don't start at zero, but then you can adjust it. So you can adjust to local context. Now, you don't have to do that every time anew, which would be impossible because you don't have the financial resources to develop a brand new model for every small town in a rural area in a least developed country, in a poor country. No, you don't have the resources, but with this modular approach, you can scale. So that's why I call the modularity a big benefit to context scalability. You can adapt it to the local context quite quickly and satisfy actually the local needs. And that's a big advantage of agent-based models, of computer simulation, and of computational approaches in general, instead of working with these broad-brushed aggregates, factors, and variables. This brings us to our last point, what I call probabilistic humbleness. What do I mean by that? I think I best explain that just by running you through an agent-based model. The best way is to get your hands on it. So this is a simulation of ants. So we have an ant colony here in the middle, and this ant colony looks for food. We have 3 food sources, one closer, one a little bit further away, and one furthest away, and the ants randomly walk around. They cannot see, they don't have any vision, they don't know where they're going, they're just doing a random walk, just like, dumb little ants. And when they find a food source, they most quickly return home. Then yes, they return home, and on their way home they excrete this pheromone. That's actually how ants work. They excrete this kind of chemical, and other ants like this chemical, so they stay in this chemical cloud once they can perceive it and say, well, that smells really good. That increases their likelihood of also finding the food source. Now, this chemical disperses over time, so we need a critical mass of ants, but the more ants go attracted or get stuck at this chemical cloud, you can see now they depleted the first food source, right? So the first food source is depleted. Now again, they randomly walk around. They see, oh, they found the second food source, the second closest food source as well. They build a little transportation way there, and now again, they randomly walk around. And now we have a critical mass, do we? Yes. To build a bridge to the third food source as well. Enough ants get stuck in this chemical cloud. The cloud disperses once everything is done. And yeah, we can make predictions. So the prediction here would be to say, if you run that again, well, my prediction would be first you deplete the closest one, then you deplete the second closest one, the one down there, and then you deplete the third, the furthest one, which is the furthest away. And you can run simulations, and most likely that's what will also most likely happen. If you do an analytical model, your favorite math model, on average, that's probably what your assumptions would lead you to as well, if you optimize that model at the end and look for the optimal. So let's run that again. We do another numerical simulations. We see our ants randomly walk around. They find the closest one again. They find the second one too. And now they're exploiting both at the same time. And check out what happened now. What happened now is the middle one got exploited first. Well, that was unlikely, but it did happen. It did really happen. I just saw it happening. And then they go to the second one and deplete this one. And then they still walk around and find also the third one. So now we have, the order was not 1, 2, 3. The order was 2, 1, 3 of the depletion. Was less likely, but it happened. Let's run it again. Let's see what happens now. Ants walk randomly around. You can see they found the first one, they found the third one as well. Well, no, they really set on the first one. They all go over it. And yes, our predictions are holding out perfectly. The closest one first. They found the second one, good. And now, a group of them, check that out. A group of them now discovered the third one too. And they're really going on the third one now. Yes, they're really going on the third one. Most of the ants get stuck there, and they depleted the third one. Second, so now it goes 1, 3, 2 in this sequence. Our predictions didn't hold up. Now, I also wanted to show you a version, honestly, where the third one got depleted first. And I run it several times, but eventually I had to move on. It will happen. It will happen as well, but it is true. It's very unlikely that will happen. Now, fact of the matter is, to say it in some prosaic words, that history, life, is just one damn thing after another. This famous quote is attributed to many people, among others, to Churchill and so forth. And that's what it is. So it might be that something is very unlikely, but history only needs once. And I invite you, this model is in the models library of NetLogo. Please go and check it out. It's called ANTS. You can run it and maybe you'll find it. You find the likelihood also, and you find that when does it happen that the third one gets exploited first, the third food source. And once it happens once, it can have important ramifications. Murray Gell-Mann, one of the co-founders of the Santa Fe Institute, Nobel Prize winner in physics, calls these frozen accidents. That's when something happened, one damn thing, and everything that comes later on is affected by that. So that's what he calls a frozen accident. And he says most single accidents make very little difference to the future. But others may have widespread ramifications, many diverse consequences, all traceable to one chance event, maybe very unlikely, that could have turned out differently. Those we call frozen accidents. The accumulation of frozen accidents is what gives the world its effective complexity. So he says the structure in the world actually comes from that something happened. It was unlikely to happen, but it completely changed the course of history, right? Future just went into this fork and split, and we went down this part. Might as well have gone down this part, but we didn't. Now, it might have been unlikely, and your science of averages, of homogeneity, would have disregarded that completely just because it's unlikely. History doesn't care. History only runs once. So we cannot do big averages here, right, if you want to explain that. Now, another way of saying that is the science of the history that didn't happen. So instead of doing beautiful Newtonian physics, so by comparison to a beautiful Newton-like generalization, actually history is just this particular apple bobbling down this particular hill. So while the apple usually rolls down the hill, pulled by gravity, it's just this particular apple, and you cannot really say how this apple, that's Epstein said that from the Sugarscape model that we worked through. It rolls down a particular way, and it's really difficult to predict. You can make this generalization that give you an idea to think about it, and that's what models are good for. But in order to make this particular prediction, well, it's just probabilistic. And that's what makes you actually pretty humble if you understand that it's always probabilistic, because you would have to model the universe one by one. You have to use a one-to-one map if you really want to model what it is. But since you abstract, you lose some of the details. You always have to introduce some probabilities, because then you don't have the details anymore. So if you program your agent-based model, an agent goes to the street corner, well, you would have really, like, if the person turns left or right, it's kind of like, well, most of the time the person turns right, but sometimes the person turns left. Now, you would really have to simulate every neuron, every experience that this person had that creates this neuron, that gives this free will. You will not. So you will just average over and say, like, well, most of the time, let's say 60% you turn right, and that's a generalization. You lose the details of it. And that's where these probabilities actually come from, right? And that also allows you then not to make particular predictions. Now, the predictions that you have, if you want to explain or predict something, you have to distinguish. You can still predict the probability distribution. For example, on the Sugarscape, we could say there are very few rich people and many poor people. But we couldn't actually say which person is rich and which person is poor. Like, that would have been more difficult, but the outline of the shape we had, same with earthquakes. We can say an earthquake is also distributed to this power law, and you can say, well, earthquakes will happen, very big earthquakes will happen very rarely, but unfortunately, you can not really predict when they will happen. Now, it turns out from a bird's eye view, yes, there's a very predictable distribution of earthquakes happening, but the particular earthquake you cannot predict. Now, once it happens, you fit it in and say, perfectly fits in. Creates this beautiful macro pattern of my distribution. So the outcome of that is called an invariant stationary distribution that we have. And that's because, you roll the dice. If you roll the dice, it's a probabilistic event and they turn out to something. But on average, you know that if you roll two dice, the sum of these two dice is 7. So the sum of them, the most likely outcome is 7. That's just because 7 is the most frequent combination. It can be 6 and 1. It can be 2 and 5. It can be 3 and 4. It can be 4 and 3. So most outcomes end up in 7. That's why it's the most likely outcome. That doesn't mean that you can have 2 1s or 2 6s. I mean, there's only one way you can have 2 1s, but it can still be an outcome. So you have this distribution that's called invariant distribution. If you run, for example, Schelling segregation model, and you run it many times, we saw every time it's a different outcome, a slightly different outcome. So segregation is 85.8, 86.5, 87.5, but in kind of like in the ballpark, same as with Sugarscape, the income distribution is not always exactly the same, but we saw, for example, these 4 terraces that we have here. So you have this at the end, we call this the invariant distribution. And in order to get that, you have to run your model many, many times, because the more often you run them, the better picture you get. That's because of the law of large numbers. So, for example, if you have only 4, you roll the dice 4 times, you get not a complete picture of what's actually happening. You roll it 16 times, 32 times, and these agent-based models, we run them hundreds, thousands of times. We let them run overnight, go home and sleep, and the next morning we have run them many, many times, and we get these invariant distributions. So the outcome is probabilistic. You can say it's more likely that the closest food source is eaten first, and the more distant is is eaten later by the ants. But at this particular historic event, we cannot really predict that because it depends on the interactions of all these other probabilities that we don't have the details. We just convert them, which leads to this invariant distribution at the end. And I call this humbleness because since I'm today chatting away about policy making, let's bring that back to that again. That was also my experience. You're in this world of policy making. You go there and say, Mr. President, and you hear these other consultants that go into this president's house and try to go into this ear and try to talk into this ear and say, Mr. President, if you do this and that, this will happen and this will get you reelected. And that is not how it works. You cannot say ever in science, if you do that, that will happen. It's not deterministic, it's always probabilistic. And that's actually more humble to say, Mr. President, if you do this, the probability of that desired outcome is 60%. But there is a 2% chance that it really goes wrong. Now, I don't know. I ran it 10,000 times, and I think 2% is what it is. We run it once for you here with this real society, it might go really wrong. Because 2% is still a possibility, right? The good thing as a scientist that there's a researcher at the end you can say, well, told you so. No, you should not say that, but you have to be open and very humble. So instead of when you hear politicians saying, we do this tax reform, and it will increase it will create so many million jobs. And we do this health reform, and it will get so many more people on healthcare. This is not correct. You can never say that. You can only say we do this health reform. The best informed abstraction from reality, which is actually a pretty big abstraction, leads us to expect that if we do this, there's a 60% chance of this happening, a 20% chance of that happening, a 5% chance of this happening, and right? That's the only thing. So that's why I say these computer simulations, they actually visualize and visualize this probabilistic idea of science, and all science is probabilistic because of being an abstraction. And it makes you actually more humble as a scientist making predictions. That wraps up the part where I wanted to tell you about some of the characteristics of agent-based computer simulation, which kind of makes them special among the scientific methods and research methods that we have available. That brings us to the next point, outcomes. And the outcomes, as you already know, can be quite surprising, as you can see here. And the good thing is that while they can be quite surprising, there are different kinds, different classes of outcomes of computers, and there are only 4 classes. I'm piggyback here on a very, very influential book, A New Kind of Science, from Stephen Wolfram. And these are these 4 classes basically of all kind of models. It's a little bit pseudo 4 classes because there are many more, because the 4th class is a little big, but okay, let's start like that. One class we've already seen of the possible outcomes of any kind of model, especially an agent-based computer simulation, and that's a homogeneous state or an equilibrium. So we saw that in Schelling, for example. So that means the model evolves into a stable homogeneous state, and any randomness of the initial pattern actually disappears. So in Schelling's model, we went to this state of this level of segregation, and that's when it stopped. You can run many times, and that's where you can make your invariant distribution, your stationary distribution. Out of this, the accumulation of these different equilibrium states, which always might be a little bit different, but at the end it stops and it gives you a clear data point. Segregation is 85.6%, for example. Now, another possible outcome is a cycle or periodic orbit. So the model evolves quickly into a stable or oscillating structure. Some randomness might still remain, but there is a clear cycle with it, what is called a periodic orbit. So for example, you have day and night, and day and night, that's a periodic orbit. Or you can have 3 different states, it oscillates among these 3 different states, or you have winter, spring, summer, fall. Or in the economy, some kind of cycle goes up and down. You can see these cycles, and it's not like it stops at one point, but you can make a prediction about these cycles, and there are special methods you can use to analyze this kind of periodic behavior. That's also a possible outcome that you can have. Then another outcome is randomness or apparent randomness, chaotic behavior. So you can start with a completely deterministic process. The process is very well defined, but you lose too much information on the way and you cannot track, for example, the initial conditions. And if it's sensitive to these initial conditions, the initial conditions that you started with, you cannot make any predictions anymore. You lost all the information on the way, and these are called chaotic systems, but at the end also, for all practical purposes, are random, apparently random. So the model evolves in a random or pseudo-random, because actually they're still determined, but for you as the observer they are random, or chaotic manner. And any stable structure are quickly destroyed by interactions with the surrounding noise and lack of information. Now, honestly, if something is really truly random, you cannot really make predictions, especially predictions that are often useful, because if there are two different events and they're uniformly, like, you can make predictions on the level of the distribution, on the level of the random distribution, and you can say, well, there's a 50-50 chance, but you cannot predict anything beyond that. You can say there's a 90%, 10% chance, but beyond that it's random. So the level of science then gets restricted to this higher level of distributions. And last but not least, and that's why I said it's kind of like a pseudo 4 categories, because the last category is extremely big and this is complex. And same as the non-linear, it's kind of like the zoology of non-elephants. The complex is kind of like an aggregate term where there are many different things thrown into that we do not understand yet. And computational methods help us to dig a little bit deeper into that and try to piece it apart, make a taxonomy of these different complex patterns. But basically, the model evolves by forming local structures that interact in complex ways. And they're able to survive for a long time. So you also might be at the end part of a periodic orbit, for example, but it might be that a cycle takes, 8,000 years. So nobody ever observed one, right? Because we didn't document history before 8,000 years. And it might be in some cultures are more in the cyclical worldview. It might be that history returns itself. We just wouldn't know at this point. And for us, it seems like, there seems to be something that's going on, and we can still make some kind of predictions, but for now we don't know. So it might be that it's part of something different, just to say like one aspect of it. And they can survive for a long period of times, also these local structures that help you to make predictions, but then again, you might lose them, right? So they're not random, but not also clearly determined. They're somewhat predictable. So let me walk you through an example here with one agent-based model, which is based on the Lotka-Volterra equation. It's predator-prey dynamics. And we start with one model where we have a predator and a prey, and that will get us to the homogeneous equilibrium state. So we have wolves here and sheep. Both walk randomly around. I have 100 sheep and 50 wolves. They walk randomly around, they're blind. The wolves lose some energy with every step they take, and they can run out of energy and then they die. Or they randomly find a sheep, they will eat the sheep, and with that replenish their energy as well. And the idea is now, well, how does that evolve over time? They also have a certain reproductive rate if they survive then. And you can see here, first of all, we start out with more sheep, twice as many sheep as wolves. The red line down here is the sheep, the black line is the wolves, and the sheep keep on increasing. So the sheep flourish, there are more sheep than wolves, so they have an advantage, they can flourish, they can reproduce better. And you see, as the sheep increase, also the wolves will increase, because now the wolves have more food. Now, if they have wolves have more food, that's great. The wolves went so big that the wolf population went so big that actually the sheep population started to decline. The sheep population started to decline because there were too many wolves. Well, that's bad for the wolves. And now you can see here in the graph that tracks the number of sheep and wolves. The wolves also start to decline because there are not enough sheep around anymore. Now the wolves start to die out. But the sheep bounce back. The wolves are also gonna bounce back then, right? There's still some wolves around. Well, then now there are enough sheep for them to find. Sheep are increasing, but the wolves now, the few wolves that survived that, also now have way more than enough food. So they are really in a luxurious situation right now, running into sheep every step they take, and they really start to populate. They start to populate so much that they crushed the sheep population. Actually, that's something humankind always struggles with, right? We are often prone to overdo it. Now, what will happen if you overdo it? Well, now the wolves have nothing to eat left. They really overdid it. They have nothing to eat left, and yeah, they're going to go extinct. Kind of like killed their necessary resource by being way too greedy. And there's still some wolves around, but eventually, if there's nothing to eat, they will go extinct. They will die. One lonely wolf. That's what we have left. And at the end, well, that's an equilibrium state. That's a homogeneous state. Nobody survived. Right? That's an outcome. And that's an attractor that they can be attracted to. Let's run it again to see if we get the same result. Again, our sheep start to increase. We have twice as many sheep as wolves. That's just how we set it up. You can play around with it. You will find it in that logo library. The wolves increase. They almost kill the sheep. Oh, you see, some sheep survive. 2, 3, 4th sheep, they just didn't run into these wolves. These were some 2, 3, 4 lucky sheep. They didn't run into the wolves. The wolves didn't find them. The wolves died out. What happened now? The wolves died out. Wow, feel free to go back and replay that one. The wolves died, and what happens now with the sheep? Well, they have nobody to prey on them. They basically, well, that's a lot of sheep. The sheep inherit the earth. Yeah, very funny net logo, very funny. But the sheep inherited the earth. Yeah, that's what actually happened. Let's try to do that again. Same, first the cycles at the beginning, we see the same. The sheep goes, the wolves go, and what we find here again, the sheep died out, we find one equilibria, nobody survives because the sheep didn't make it. And the other equilibria that we can find, the other homogeneous state that we can find, is that the sheep inherit the earth. Because you can see here, a few sheep are still around, the wolves don't find them. These 3 sheep, wow, these 3 sheep are still around, make it, the wolves, it's too sparse, the wolves don't find them. No, there are 4 sheep, they bounce back, but it's too late. It's too late for the wolves. The last wolf will die out, not close enough to the sheep. And now, well, nobody can stop the sheep anymore. The sheep will inherit the earth. So, but that's another equilibrium homogeneity. So we have these are called attractors. These attractors that the system gets attracted to. Either the end state is all sheep or nobody. And in this model, these are the only 2 solutions. Now you can have an invariant distribution, and I have these terms here because some people call it differently, depends if you're from physics or from some other discipline. So it's an invariant distribution, a stationary distribution, an invariant measure, a stationary measure, so a mix of this. But that's the idea. In this end, we don't have this distribution that I showed you before. We just have 2, and it can be 40% of the time this happens, 60% of the time that happens, right? These 2, and that's one possible outcome. And that's quite frequent, as we saw, for example, in shelling models, that you have this. It's very good, because then you can make pretty good predictions if you have these attractors. So look at another model, cycle. So the cycle, the idea is that something goes around in cycle in a periodic orbit in a season, for example. A season is a cycle, an economic cycle, they're actually called cycles. And here what we introduce now is we get rid of the wolves, but we have the sheep dependent on grass. So the sheep eat grass. The grass doesn't move around. It also when it gets eaten up, it replenishes as well. But the grass doesn't move around, which gives us a little bit of different dynamic. And you can see we get cycles here. The grass goes down as the sheep increase, and they balance each other off. We have less grass that affects the sheep go down. If we have less sheep, the grass can grow back. If we have more grass, the sheep say, yay, let's go for the grass. So the sheep go up. And how the system is established here, how I basically set it up, we get these very smooth cycles. Do you see it in the monitor down there? We get very smooth cycles. The sheep fluctuate a little bit more than the grass because they're dependent on the grass. One follows also the other. The grass goes a little bit first. You could say the sheep follow it because the sheep prey on the grass. They are the predators, but you get a very smooth periodic orbit, a very smooth cycle in this, and that also gives you predictability. You can say, well, this happens and this happens, same as you can predict after day comes night, and after summer comes fall, and then comes winter. So you can make predictions with that, but it's not like you get pulled to one attractor and you stay there and nothing else changes anymore. You're in equilibrium. Equilibrium means that nothing else changes anymore. Right? So that's another outcome that you can have. in complex adaptive systems, which are very well modeled with agent-based computer simulations. Then again, the random, as I said, well, honestly, if something is truly random, you don't have information, you cannot do science, really. So we're gonna skip that one for now and go to the last one, which is where we need all of your help as future researchers, which is the system is complex. And social systems are complex systems. So now we bring all of that together. We have our grass, and our sheep eat the grass while the grass grows back, and our wolves prey on the sheep. Right, so we have a 3-variable problem, interdependent among them, and we start our simulation, and we can see here at the bottom, we have a lot of grass, so the green line, that's the amount of grass. The sheep increase, yes, the sheep and the grass, they balance, we saw that. The grass goes down, the sheep go up. When the sheep go but if there's not enough grass, the sheep go down. Okay, so these two fluctuate. We've seen that cycle. Well, now, but the sheep also depend on the wolves. And the wolves now prey on the sheep, which means the sheep go down. Now, if the sheep go down, as right now, the sheep go down, the grass can go up. Now, if the grass goes up, the sheep should bounce back. But if the sheep should bounce back, then the wolves also increase, which affects the sheep. Which then, if the wolves increase, the sheep will go down, which allows the grass to go up, right? So it's not like a smooth cycle. The wolves really mess this smooth cycle up, but you can see something. There is something predictable. There's certainly a trade-off between grass and sheep. We can see that clearly. And the wolves, and there's also a dependency between the wolves and the sheep. You can also see that clearly. I mean, if the sheep go up, the wolves can thrive. But like the best you could describe that, it's say it's complex. Now, it's not complicated in a way that's really complicated. We only have 3 variables here. It's not tremendously complicated, but it's complex. You can make some predictions, but not really perfect predictions or not smooth predictions. There is randomness still involved. Even so, there are some local structures that you can identify. And often that's what you most often find in social systems, complex adaptive systems, and ecosystems, of course, as well. Now imagine in society or in ecosystems, there's not only 3 variables. Right? That's a quite simple model, and you already get patterns like that. Now, try to make predictions in reality with society. That, yeah, the best thing you can say is complex. So that brings us to our last one. And these are the 4 outcomes. I just wanted to show you to them. So you have, it's not like anything can happen. Even so, the last category, as I said, we will need all your help to dig a little bit deeper into the different kinds of complexity, but homogeneous and equilibrium, where you then, every time you run it, you might get a slightly different attractor. In the Lotka-Volterra model, we got 2 very clean ones. Either they are only sheep, or there's nobody. In the Schelling, we also got equilibrium, but they were always a little bit different every time you run it, so you get your invariant distribution, your stationary measure. Then there can be a cycle, up and down, very, very nice and smoothly. A lot of systems work with that, and that's very useful. Economic growth and recession. Economic growth and recession. We can actually measure them as well, and we've seen them over hundreds of years now. Randomness, truly chaotic. That's a tough nut to do science. That's a tough nut to crack to do science with. And then complex. That's actually the biggest group where we can see most of the patterns in, especially in social science. And that brings us to our last point, and that is, what are some critiques of agent-based computer simulation? So you develop your model, and you're really excited about it, and you bring it to your CAO of the company because you have this new strategy and you have enough evidence that will change the course of your company and capture all the markets in the world, or the government, you want to change a law, or as a researcher. And then once you come up, of course, there comes this old, white, male professor who says, well, that's interesting. Wait, okay, hold on. I'm going to be an old, white, male professor. Well, hopefully I will be. But I still hope I'm still going to be open-minded. I hope that I'm still going to be open-minded. All right. So there comes always this critique. And I'm like, oh, yeah, that's interesting. That's interesting, but. And conversations I had with Robert Axtell, that's the one who programmed the Sugarscape that we worked through in another session. We had an interesting conversation about that. And he actually also reported some of the critiques he's always getting is doing big computer simulations, social computer simulations. And that's one of the critiques that you always get. Is your model is interesting, but it doesn't have the rigor of a mathematical model. So there's kind of like a little arrogance about like, no, science has to have a mathematical model, these beautiful equations, and you're just playing computer games. Right, and that critique actually comes in different versions and in diverse variants. For example, well, we've long had such a much more elegant and a much less messy analytical model, for example. Or another variant of that would be, well, I don't see how this relates to this beautiful simple equations that I learned back in school many decades ago, and we already have that. So I just don't believe in it, because I don't see how that relates to what I have known to be the truth. So these are some of the variants, and now these are critiques that also might have some validity, but I want to talk about what would be some possible response on that in defense of computational methodologies. Well, first of all, so here we have our beautiful equations, a differential equation of Schelling segregation model, for example, and here we have the same just in code. Now, they're actually equivalent in a sense. This code basically codes up these equations, and these equations summarize what this code then actually does. So there is a mathematical basis. There are equations. It's just our equations are written out in code and not in differential equations. To say it in the word of Joshua Epstein, the other co-author of the Sugarscape that we talked about a lot, he says, the often claimed distinction between computational agent models and equation-based models is illusory. Every agent model is a computer program and is such an explicit set of mathematical formulas. In practice, these formulas might be extremely complex and difficult to interpret. But they surely exist. I mean, they surely exist. You write this code down, or you can read this code, and this is your equation. And sometimes it's easier to just run it and have a numerical solution. By the way, then if you solve your differential equations, you will get a beautiful analytical solution if you can solve them. And the numerical solution, if you just run your code and see what happens, is an approximation, is a discrete approximation, for example, of that. But as a fact of the matter, even if you do differential equations, and I say that, I talk to those of you who have done differential equations, even if you do differential equations nowadays, you solve them on a computer, and they're also just numerical approximations. I mean, a computer is a discrete computing device. What the computer does is also just run simulation. It approximates it through a discrete approximation, right? Your differential equation. So if you've never done differential equations, no need to do, and never mind what I just said, but to have the understanding. So if you do anything with a computer, it is basically a computer simulation already, and very few people nowadays do still even differential equations by hand. So yes, it is still a mathematically very solid base. So there's a strong argument, and you can actually defend that. Equations are not better or worse than code. It's just a different kind of code, and the equations are written like this. To walk you through an example of this, a related critique is that, well, we have this elegant, beautiful equation, and you have this messy numerical solution that actually every time gives you something different. It's just as messy as reality, I would say, is a short response. But let me walk you through one of the main benefits of having these messy numerical solutions. And the example is from Hotelling's law. Hotelling's law is a very old law in economics from 1929. And what Hotelling analyzed is how different companies divide up the market among themselves. So how they try to maximize profits by adjusting their prices and capture more market more market share. So here, for example, that's a net logo simulation. You have two companies that offer products, and what these two companies do if we run the simulation, they first increase their prices, but they also move closer to each other. So as they move closer to each other, they start to compete on the basis of prices. So here in the upper monitor, you can see the prices. They destroy both of the prices. The prices go both down. They find a minimum price where they they've destroyed their market by trying to compete too hard. And you can have different results there and look for optimums. And hoteling, again, really great work, did that with pen and paper, with two companies. Here you can see the original paper from 1929, and worked out these beautiful graphs, and it became a very standard law for us to understand better how are markets actually divided and how does competition among products affect the price and the market share and so forth, and what can be the result. Now this was done with two companies. The cool thing with computer simulations is on a click of a button now, let's just make it 10. Let's make it 10 companies. So let's see what happens if you have 10 and you run that. You can see, oh yeah, they compete. Some of them, yeah, they drop in price in general, but some of them are pretty profitable. You can see the two green ones and the yellow and the red one down there. They kind of like have this two dynamics, so these are the two who actually compete with each other. Oh, down there on the other side, the purple, the blue, and the pink, they basically compete among the three, right? So the three among them compete. The two green ones are in a pretty tough fight there. And the purple one didn't get interested anymore. So the purple one kind of like left the blue and the pink. The orange one seems to be in a very comfortable place. So the orange one is in a pretty comfortable place saying, I found my niche, here I am. If you would try to model that with your favorite mathematical equations, I would say good luck. Honestly, I couldn't do that, and it's extreme. Now imagine doing that not only with 10, with hundreds of companies and interacting equations. And so, as messy as reality is with these computer simulations, you can pretty easily extend it to realms where your analytical mathematics runs basically into unsolvable problems. So what you often do, what we did here, is you have your standard model, and the standard model describes something very beautiful, very discrete, which gives us great intuition, and an analytical solution is extremely powerful. Because once you have that, you can make very good predictions. It will go there, right? And the agent-based model kind of like expands it. That's what we did here. We expanded Hotelling's law by a computer simulation. And that's great. So that's one of the contributions that these messy simulations can contribute to science. Now, the other way around, how you often also start, is you have a standard model that explains something, a standard theory in social science, and with your agent-based model, you replicate one specific part of it. And then you can really look under the hood, and this one specific part you can understand very well. That's how you often start a research project, and that's great to learn. Doesn't really advance our knowledge too much. So if you would like to publish that, or go to your CAO, or go to a public policy decision maker, they would say, like, yeah, we already know that. That's okay. Come back until we know something else. What is more difficult, so that's not really so useful. Another thing is that you sometimes find is you see the standard model of something that happens, a standard theory, for example, in social science, and you play around, you set up an agent-based model that is not really connected at all. You just find something completely different. Now that's a very hard sell, because there are these old male professors that make it really difficult. That make it really difficult to all the CAOs who've seen it all, the policymaker who's done public policy for 40 years. So that's a difficult sell, honestly, if you go with that. So it would be better to kind of like bring them together, right, and have an overlap, and then expand, and in the best case, do what I showed you here. Have a standard model, have a standard sales strategy in the company, and pick up on this sales strategy, what has been proven, what works, and then use computer simulations to show that actually, well, we can actually model more complex reality than the standard common wisdom that we have. Same in public policy. There's one policy that worked well and we understand it well, and now we can include more variables in order to explain more, and then you can go to your boss and say, well, now we learned something new. And that's a very big benefit of these, and that's one way how you can encounter these critiques. Your model is interesting, but We either already know that, or it's more beautiful, or it's the standard Common Core. So there's another critique you would frequently hear when you do agent-based computer simulations or computer simulations in general. So you go to your boss or to a colleague or to your peers. If you are involved in a peer review exercise in academic research, everything is peer review. That means you send your research results to somebody who don't even know who that is, another researcher who reviews that and then gives you a critique before your work can be published, right? So one thing you frequently hear an argument that goes somewhere along these lines that says, well, I'm an expert in X, and I don't believe your results because your model doesn't consider X. Well, yeah, first of all, that's bad luck, right? You didn't consider X and send it. Somebody saw that it happens to be an expert in X. But if you think back to Sugarscape, there was an awful lot of things we put in. I mean, chances that you miss something are pretty considerable, and they're experts. Now, yes, if your boss happens to be expert on something, try to put it in, right, before you present it to your boss. But otherwise, I mean, there's so many things you can consider and that we considered in Sugarscape. Yes, that's a very valid critique, and it comes in various variants as well, this one. One variant, for example, goes something like this. Well, can you put in X and get back to me? Your boss would say that. Or a peer reviewer, otherwise your graduate student, and your thesis cannot be published until you also put in X and then get back to this person who claims, and that's another variant of that, it says, well, if you put in X, this other variable, right, I'm sure you get different results. And as we also saw on Sugarscape, yes, we put in a different variables, things can change, things can be different. You change your assumptions, things can be different, you don't get the same result. So it's a very valid critique. It is important to consider things that actually matter. That's a really hard problem. Now at the bottom of it, deep down the rabbit hole, the best response to it comes from a statistician called George Box, and George Box famously said, well, all models are wrong. Actually, all models are missing something. All models are actually wrong, but some are useful. So that's a very important thing to remember. It's a very important phrase. All models are wrong, but some are useful. Well, they must be wrong. As we already said, the only real working model of the universe is the universe. Because you always abstract, you cannot model everything. So if you start out with some dynamic that you model here, and you go into a bigger dynamic, which actually derives from a much bigger dynamic, you might as well abstract in a different way. Now, which one of these two models is right and which one is wrong? Well, both are wrong. Because both are not a one-to-one map of reality, but one might be more useful than the other in order to understand something, right? So since the only working model of a universe is a universe, now the question with computational tools is, how precise can we be? Can you actually create a digital universe, kind of like the Matrix, a computer simulation of reality, a one-to-one map? So imagine like this, in a few decades, if you walk into the White House where big decisions are being taken, it won't be full of lobbyists and strategists and political scientists and economists and cultural scholars. And so it might be full of servers that basically do a one-to-one simulation about the 7-something billion people on planet Earth, simulated one-to-one, fed with big data in real time, calibrated, constantly being fed with data. Well, Edward Snowden revealed us a little bit about the data that the American government is handing. Now imagine even a few decades down, how detailed this data will be updated in real time. You run your simulations, and if you get to a clear outcome, an equilibrium, nobody has to take a decision. I mean, if that's kind of like the model that you're going with, then that's the model that you're going with. That's the assumption that you have, and that's the prediction, the best prediction that you can have. Now, if you get a probabilistic outcome, you say, well, 50% this might happen, 50% this might happen. So there are two attractors, for example. then the commander-in-chief, the president, we elect somebody, and this person then has to call the shots. As presidents say, the buck stops here, the responsibility stops here. So if nobody can decide at the end, we have to have somebody or a Congress or something that then calls the shots. But if there's kind of sufficient predictability, then yes, we don't have to make that subject of human judgment. So that's kind of like, the vision, and that's where we're going. Financial markets are using big agent-based models, fed with real data in real time, making financial predictions about the market going up and down. And now all models are wrong. All models are wrong. So it would be actually very risky to build this one computer simulation in the White House, as I told you. Since all models are wrong, it might be a little bit like this. Then we miss all of that. The model as it could be, it will never be really a one-to-one simulation, right? It won't be a one-to-one map, because then you would have to really recreate all of that. Every neuron that's going on, every quantum effect, maybe it matters, that happens inside a subatomic particle, and wow, that would be a lot. So you might want to make many models. So you might make many models, and then there's this assembly modeling. So you make many models, and then you take the average, and it turns out actually these assembly approaches to modeling, taking many models and then seeing kind of like what's the average, some with these variables x, some without the variable x, and then see basically where they end up with. And that's a very, very useful approach. Now, what we also know, and that's actually good news, and at the same time I'm going to tell you bad news. The good news is that with more computing power, and that's a promise of computational science, with more computing power, we can make more exact models. With more data, with more fine-grained data, we can calibrate our models better. And with more computing powers, we can add more variables, more rules of behavior, more complex rules of behavior, and we can run them quicker in order to find, and that gives us better prediction. That's a promise that we are after. Now, it's often not nearly close enough to really predict reality as it goes. For example, consider something like the weather. The weather, you would have many, many variables that are interacting in order to predict it, especially far out. Now, the weather, as far as we know, there's no magic involved. We understand kind of like the rules, we understand where it comes from, we understand what happens when. We studied that now for a long time, and we understand it's not magic, it's not a Greek god Thor in the heaven that arbitrarily makes sure. No, we understand that. Still, we cannot really predict it much further than a few days. We got much better in it. 10 years ago, weather prediction was extremely bad. We could actually only reasonably predict 1, 2, 3 days. Now we got much better with all the computing power, but still, weather is what is known a chaotic system. So it's chaos, and there's this what is known, there is the butterfly effect. Because you have all these different variables, even little variables. So the butterfly effect is called butterfly effect. You might have heard of it because it comes from this idea, if there's a butterfly on the other side of the globe and this butterfly flaps its wings, does that make a difference or does it not make? Do I have to incorporate that in my agent-based model? Like really, like a butterfly on the other side of the globe? But it can be shown that if you have a hurricane over here, for example, you have a big storm, it might be actually, this is also possible, the idea in this metaphor goes that a butterfly flaps its wing, that moves something, maybe very unlikely, it moves something else, the flap of the butterfly becomes a little wind, the little wind puts something else off, there's a feedback loop that then expands, it goes over the ocean, and what here turns out to be a storm. Where did this storm come from? Well, there was this initial condition, this little thing, this little frozen accident that had big impacts. And if you don't consider all of it, it's impossible, especially in chaotic systems. They're defined, but that's what chaos is. It's still deterministic. We understand how it works. We just don't have enough information or computing power in order to really get to the bottom of it. So you cannot have, we know that for a fact, is we cannot have a complete deterministic prediction of what will happen. Right? Now, we are getting better. So even with the weather, we got a little bit better. Now, not only here in California, which is pretty easy, so we are very lucky here, the weather is pretty predictable, but also in cases where it's a little bit more difficult to predict the weather. So, Summing up, all models are wrong, but some are useful. And to say it in the words of another big thinker, René Descartes, the big philosopher, he said, well, it's truth very certain, then when it's not in our power to determine what is true, and we can never know what's true because we don't have a one-to-one map, we ought to follow what is probable. It's another way of saying something I already repeatedly said is all models have to be probabilistic, and therefore all models must be wrong, but some are useful. Now, when do you know that a model is useful? Like, when do you know which variables to put in or not? There are some guidance, some methodological guidance, and one very important one, a big principle I wanted to share with you, is called and known as Occam's razor. So William of Ockham lived in the 1200 something in the 13th century, and well, his origins are as mystical as this principle of Occam's razor. There are some very concrete scientific implementations of it. Rissanen, for example, developed the minimum description length principle. If you're interested in that, look it up. But it's a principle as well. So it's not like a direct algorithm, but it's a very useful principle to find out which models might be useful. And being a razor, as you can see here, the idea is to shave away everything that you don't need. So you shave away and you shave away, and to formulate it in some sense is a model is not done when there's nothing left to add, but when there's nothing left to take away. That's the idea of Occam's razor. So the model is useful and is done actually when it's as small as possible and you cannot take anything away anymore. So the question is not what do I have to add, the question is more what do I need, what's the sufficiency of things that I need to explain the phenomena I'm interested in and to make predictions or explanations about the phenomena I'm interested in. And this principle is so important. All the big thinkers actually that we have had in human history refer to it in one way or another, and I want to walk you through a few, starting with Aristotle, 350 years before Christ. He said, we may assume that the superiority, ceteris paribus, of the demonstration which derives from fewer postulates or hypotheses, in short, from fewer premises. So he said, ceteris paribus, that's Latin for meaning all other things being equal, if you have two models and they both explain the same thing or predict the same thing, then the one with fewer premises, postulates, fewer variables, fewer rules, that's more likely to be true. And that's something you can really say. The minimum description length principle actually formalized this idea information theoretically. Another big thinker, Newton, again Newton, the big scientist of modernity, Newton, he said, well, we are to admit no more causes of natural things than such as are both true and sufficient to explain their appearances. Nature is pleased with simplicity and affects not the luxury of superfluous causes. He actually called this rule number one of his rules of reasoning. All right, so the big scientist Newton, rule number one is that nature is pleased with simplicity. Don't add bells and whistles if you don't need to. So also goes along the line of Occam's razor. Another one, Kant, again, the big philosopher Immanuel Kant. He talks about the well-known wisdom that presupposes that the rudiments, the principles, must not be unnecessarily multiplied. And it's well known. He uses a Latin phrase that is very common, saying, entia praeter necessitantem non esse multiplicanda, which basically means what he said. I did have to take Latin back in school in Germany. Many years ago. Honestly, I wish I would have learned another language that's more useful. I can talk with more people. For example, Python wasn't so popular back then, but I recommend to you also when you learn a natural language. So I speak 5 natural languages, but if you learn a programming language, which is also a language with a natural language, you can talk maximally to 1 billion people, right? If you speak Mandarin, Chinese. With a programming language, you can speak to several billion devices. So I encourage you, don't learn Latin. learn Python if you're about to learn an additional language. Very useful. If you can speak Python, you can speak with many devices, and they are always gaining importance right now. Who else? Einstein, of course. Einstein, he also, of course, adhered to that principle. He said, not without tongue-in-cheek, he said, well, everything should be made as simple as possible, but not simpler. Aristotle said that with the Ceteris Paribus, it shouldn't be simpler than what you need. It should have everything that you need to explain a phenomena, but don't add bells and whistles on top. So that's the idea of Occam's razor, and that can guide you. And there are some formal ways of doing that with a minimum description length principle. The minimum description length of your model actually turns out, and you can prove that mathematically, turns out to be more likely to be true. Yes, I mean, unfortunately, we don't have the luxury to go into that, but it's a very deep and very important principle. Now, that being said, these are all principles. That's not a recipe that you can automatically follow and it will give you to the best model. Finding the best model is still a very creative act, and it always will be. That can actually be shown. We can never prove that we found the best way of representing something, that we found the best algorithm. That's related to Gödel and Turing, if you're interested in these kind of proofs. But we can show that. You can never actually prove that. You never know if there might be something better around the corner that you have never seen. Basically, that's what it comes down to. So it will always require creativity, a lot of imagination and creativity. You cannot be guided. There's no silver bullet, no crystal ball that I can talk to you about. And that makes science, and coming also kind of like to the end of this course, that makes science an extremely creative enterprise. You have to be really imaginary and creative in order to see, like, what variables do I take, what variables do I put in, how do I represent it in order to explain to myself and to others actually what's going on. David Hilbert, the real, kind of like the real Hilbert, not like me. So David Hilbert was the most important mathematician of the 1900s, of the 20th century, and he still is my very, very distant namesake relative. He certainly didn't leave any of his mathematical skills with me. Gets me still really upset. But he was so influential, for example, because in 1900 he went to Paris and basically said, well, there are some problems that I cannot solve. And he just talked about these problems that he cannot solve. And still until today, that's basically the agenda of mathematics. If you solve one of these problems still, you get $1 million. Right? So there's still some left. You can take your shot at it. Actually, there was one solved not too long ago. It was a really hard one. But it was solved by somebody who actually, they never could get a hold of him. He was a Russian mathematician. He actually solved it in a footnote. And they had to contact him and say, well, did you say that in your footnote? And he's like, responded, he didn't respond at the beginning. But then they basically could show that, yes, he solved one of these 100-year-old problems, and they wanted to give him the $1 million. They couldn't get a hold of him. He was still living with his mother and lived like in this, in his own world. So you can take a shot at these problems, the Hilbert problems, but they are really hard. So yeah, well, maybe that's what I have from him. We are really good at making problems, the Hilbert's problems. So yeah, but he was a really lovable character. David Hilbert. Many important things are named after him. The Hilbert spaces, everything that happens in quantum spaces, for example. He helped Einstein to solve his general relativity. So Einstein brought up his formula of special relativity, and then he couldn't put in gravity. It just didn't work, and he couldn't solve the math. The math was very difficult, so he went to Professor Hilbert, who was the best mathematician, and he traveled up around in Germany and visited him frequently. Actually, if you read these letters that he then exchanged, you think he went there because he really needed the math tutoring, basically. But also he loved the cooking of Hilbert's wife, Käthe. And Käthe was a great cook. So we have these letters at home. I read them back in Germany. And you can see Einstein was just fascinated by both. So he loved going to the Hilbert's house and hang out there. Well, I'm telling you all these things, but Well, anyways, that's also an introductory class to science, and science is a social enterprise, so it's important that you get to know these kind of characters, important characters that shape science, that have shaped science and are shaping science. But anyways, he was a very lovable character, a little bit off sometimes. Yeah, maybe I'll tell you another one. So once Käthe, his wife, threw a party with she loved to throw parties. He was a little bit, in his imaginary world, but she loved to throw parties. And at one point he came down and she didn't like his shirt. So he says, well, go up and change your shirt. So he went up, and after a long time he didn't come down anymore. So Käthe went up and looked what happened with David, and turns out he was in bed. She's like, what happened? He's like, oh, I don't know. I just went up here, I unbuttoned my shirt, and while I was thinking, I just did what I always do and took my clothes off and went to bed. So that's the kind of character he was. And I'm telling you this story because there's another anecdote about him. One time he had these advanced classes in mathematics, and one time one student didn't show up anymore. And after a while that he didn't show up anymore, he started to ask the other students, what happened with the students? Why doesn't he show up anymore? And the other student said, well, actually, turns out he left university. He abandoned his university studies because he wanted to become a poet. And now he's into poetry. And Hilbert's response was, well, yeah, that makes absolutely sense. I always thought he lacks the imagination of doing mathematics. Well, first of all, that's a pretty tough response, right? Because poetry is a very creative and imaginary thing to do. And he had this dry way of humor, so he surely said that as well with tongue in cheek. Because poetry is really, we think of it as one of the most creative acts to do, to try to express emotions through words. So I have this emotion, I try to produce the same emotion in you. I try to replicate this emotion through my words with poetry, so we can both feel the same. Well, that's a very creative and imaginary thing to do. Now, imagining 27-dimensional spheres and imaginary spaces where quantum effects happen, like he did, the Hilbert space, actually that's what it's called, that also requires a lot of creativity. And actually, what this comes down to is that art and science science is a way of doing art. You can sometimes see that. Alice in Wonderland is a book about mathematics, actually, that plays around with this idea. If you're really interested in learning more about that, one of my favorite books, it's called Gödel, Escher, and Bach. It was a bestseller back in the 70s. It's about the relation between science and art and intelligence in the mix of it, by Douglas Hofstadter. So Gödel was a logician, the biggest logician actually that we had. Escher is the painter. He draws amazing pictures, self-recurring pictures, and Bach is the musician, Sebastian Bach. So and this plays around with the idea. Basically, bottom line, why I told you all of this is science is surely an incredibly creative thing to do. At the end, you have to decide what goes into model, how you want to. Same as a musician has to see which notes to put in, same as a poet has to be very careful with which words to use, which words provoke which kinds of emotions, which words produce joy and other feelings, music, how to exactly do it. You can, and the same what you do with science. So, and it's extremely, well, being in that, of course, I'm biased. I would say, yes, it is incredibly creative. Probably the most creative thing you can do, trying to explain something about reality to other people through, at the end, it's models, and all models are wrong. But some are useful. That pause was intended. All right, so that wraps up the session for today. We had 3 questions as always. The first was, what are some of the characteristics of agent-based computer simulations? What are the outcomes of agent-based computer simulations? And what are some of the critiques of agent-based computer simulations? And honestly, also, I agree with many of my colleagues that say computer simulations, wrapping that up today, are until now the most complete modeling tool that we have. You can throw empirical data into it. You can do a lot of analysis and hypothesis testing. And you can do theory about realities that never existed in history, but you could imagine them. And while all other modeling tools have some limitation, your favorite mathematical tool, whatever you choose, has some limitation, differential equation with game theory or discrete methods, matrix algebra, another analysis, a social network analysis, all of some limitations. At the end, you can do all of them, your game theory and your network analysis in a computer simulation. And at the end, try to create a one-to-one model, which, as I told you, you never will be able to, but we get a little bit better and our predictions get better. And the social science is becoming more a science. We can now make predictions with 80%, 90% accuracy. We can implement policies that actually have an effect, because we can test them out many times before. We are not as ignorant anymore as before, because the computational power helps us to run them and to test them out. So computer simulations is the most complete tool that we found, but I hope I also made clear that it's not a panacea. We will need a lot of help. I hope many of you will join us in this effort, be it in academia as researchers, be it in the private sector, in the public sector. There's a lot of social dynamics to be discovered. That also kind of like now wraps up the course. It's been a long course that we worked through, and now at the end we went a little bit deeper and deeper down the rabbit hole. And I think it's important to have this big picture. That's why I went out to these kind of more philosophical topics. And I hope you enjoyed it as much as I did.